the last section where we're going to be looking at the theory of light scattering, we're going to be looking at Mie theory. Unlike the other three approximations which we looked at the Rayleigh, Rayleigh-Gans, and van der Hulst, Mie theory is an exact solution. So the advantage is going to be that we get exact solutions, and in particular, it's a very powerful theory because it applies to any particle size. It can be a small sphere, a very large sphere. It could have any refractive index. It could be weak scatterer, very efficient scatterer, but Mie theory takes care of all of them. So it's very powerful. It is limited to spheres, however, so you can't deal with any other shape. Because you get a very complicated solution, it's a numerical solution, it's not an analytical one, you don't get a lot of physical insight into what Mie theory can predict. You can you just have to run your computer programs and see what you get. So there's pluses and minuses to it. It was developed about 100 years ago by this good fellow over here, Gustav Mie. He published in 1908. He wrote a paper where he looked at this particular problem. If he had a sphere scattering light coming, say, from left to right, if you have a plane electromagnetic wave, these would be look at the electric field lines as they are affected by the sphere. And what he did is basically he solved Maxwell's equations for this particular physical problem. So he took Maxwell's equations of light traveling in vacuum, he put a sphere in their path, and what that meant is that at the place where the sphere meets, there's a boundary with a vacuum, there's going to be a bunch of boundary conditions. So there's going to be some restrictions on what the electric and the magnetic fields, how do they transition from the vacuum to the sphere. So that's, I don't mean for you to all remember this and understand it like deeply, but I just wanted to show you this slide so at least you have some sense of where the theory comes from, that it's not completely some magic black box that gives you some complicated result. So it's really Maxwell's equations applied to the case of a scattering sphere. So that's where the theory comes from. A few mathematical definitions before we get into the exact solutions. You need to define the coordinate system of the scattering object we're looking at. So what we're going to be assuming is we're going to be assuming the light is traveling along the z direction, so coming here from bottom left to the top right towards the z-axis. The scattering object will be right here at the center of the origin. And we're going to assume also that the light is polarized. So when the electric field of the light that's coming this way is going to be originally oscillating up and down parallel to the x-axis. So those are the starting assumptions of Mie theory. Polarized light traveling along the z direction and with an electric field parallel to the x-axis. And then two important parameters that we need to define for light scattering are the scattering angles. We've talked before about theta when we talked about Rayleigh scattering. That's a polar scattering angle, and it's the angle that if this red arrow corresponds to the direction of the scattered light, it's the angle that the scattered light wave makes with the original direction, which was the z-axis. So that's the polar angle theta, and phi is the azimuthal angle. So if you fix theta and if you rotate around a circle, that's also a different type of angle, and that's called phi. And then mathematically, the other thing we need to define is called the scattering plane. That's a plane defined, you need two lines in order to define a plane. And in this scattering problem, the two lines that we are considering are the incident vector of the wave. So this k would be the incident wave vector, so for the wave traveling along the z-axis. And then ks would be the vector of the scattered line, of the scattered vector, of the scattered light. So light comes this way, it gets scattered that way. Theta is a polar scattering angle. And these two lines, ki and ks, they define a plane, which is drawn here in yellow. So if you just draw a plane that will capture both of those two lines, that's known as a scattering plane. And it's important to understand the idea of a scattering plane for Mie theory, because what Mie theory gives you is summarized in this a little more complicated diagram. But basically you still have the scattered light defined by an incident k vector coming this way. It scatters at the center going off in this direction. So now the scattering plane is defined by this blue triangle over here. So this would be ki and that would be ks. So if we join these three in a triangle, that's the plane, the scattering plane. And what me theory gives you is what is the projection of the scattered electric field, so that would be this red arrow, along a plane, along a direction parallel to the scattering plane, that would be ES2, and on a direction perpendicular to the scattering plane. So let me just restate that so that it's clear, because this is the heart of me theory. So you start with a plane wave coming from bottom left towards the middle over here. It's polarized, it's linearly polarized, so the electric fields are only oscillating up and down as they travel, parallel to the x-axis. And once it scatters, that electric field is going to point in some direction. So here it's arbitrarily defined as ES. So what me theory will give you are these two values, ES1 and ES2, which are the projections of the scattered light parallel and perpendicular to the scattering plane. And once you define the scattering plane, you can also define the projections of the incident electric field along the scattering plane, that would be E incident 2, and perpendicular to the scattering plane. So that's the basic problem that me theory deals with, and that's summarized here in this matrix formulation, where it says that the intensities of these two scattered electric field amplitudes, ES2, ES1, and again, so if you recall, ES2 is the one that's parallel to the scattering plane. So it will give you what these electric field amplitudes are, and if you recall, if you square an electric field amplitude, you get the intensity. So ultimately, me theory will be giving you what are the intensities of the scattered light, and it gives you those intensities as a function of what those electric fields are coming in. So these are the incident electric fields, parallel and perpendicular to the scattering plane. And then this matrix over here, S1, 2, 3, and 4, this is what me theory will give you. So what these are the components that will map the incident electric fields to the output electric fields. So what is the scattered electric field for any given input electric field? And these are things that are going to be vary as a function of the diameter, the refractive index, the wavelength. All of that good stuff is going to be embedded in these values, S1 through S4. And this term over here, we're not going to fuss about this in this course, but I'm just going to mention qualitatively. This is a representation of a spherical wave. We've talked a lot about plane waves. This just happens to be the representation for a spherical wave, corresponding to the fact that once light, if you have a plane wave that's coming and striking the particle, once you excite this dipole, or this electric charge, it's going to be radiating in all directions. And so by radiating in all directions, it's got the basic form of a spherical wave coming out. So that's a basic formulation. So as I said, the key is going to be in calculating what the paper that Gustav Mee published was, how do you calculate these terms using Maxwell's equations? This particular matrix in the jargon of light scattering is called the Jones matrix, and this is a general equation for any shaped particle, but if the particle happens to be a sphere, which is the problem that me treated, it turns out that the S3 and the S4 terms go to 0. So then the only thing you have to calculate is S1 and S2. So to summarize, me theory applies to spheres, scattering polarized plane light waves, and it's going to give us what it's going to calculate is what are these S1 and S2 terms, which will tell us the amount, how much amplitude of the scattered wave will be parallel and perpendicular to the scattering plane. And once we know the scattering amplitudes, we can square them and get the scattered intensity. So a little bit of scary looking formulas, but I'm going to try to make them less scary looking than they seem. So this is basically the core equation of me theory. So I just wanted to show it to you again, so you get a sense of where these are coming from and how they may be calculated with a computer. So U and V, these are going to be corresponding to those, to the amplitudes of the scattered waves, parallel and perpendicular to the scattering planes. And what you can see is that each of these components is an infinite summation. So this is where we have, that's why we talk about Mie theory being a numerical solution. It's not an analytical solution. It's an infinite series. And the terms inside of this series have these two terms. They have this angular dependence that depends on the polar scattering angle. So these P functions are actually Legendre polynomials. And then you have these Bessel functions, which are related to the fact that you have a spherical wave scattering from the scattering center. The scattering waves, they can be approximated if you go far away enough from the particle. These Bessel functions can be approximated by this exponential form, and that can be pulled outside of the summation. So at the end of the day, what you're really dealing with is to calculate the parallel and perpendicular components of those the scattered fields. You're going to be having an infinite summation of Legendre polynomials. So again, this is something that is very hard to do manually, but nowadays we have computers that we can make them work for us and do all that boring hard work for us, and we just set a for a computer to go to, well, maybe not to infinity, but they can definitely do lots of terms in the series to get an accurate enough answer, and there we go. And it saves us a lot of grief. They do the work for us. So there we go. Mie theory has to do with infinite summations of Legendre polynomials, and like any summation, how many terms you include in the summation will affect the accuracy. So sometimes if you go ahead, if at some point you're programming your own Mie codes, one of the parameters you're going to have to fuss with is how many terms do you put in your summation. If you put too many, you might make the program slow. If you put too few, you might not get an accurate answer. So there's a little bit of an art in figuring out how much you're going to be, how many terms are you going to include in the summation. But in general, that's something that it's not, this has been around for 100 years, so people have a pretty good understanding of how many terms depending on what size particle and wavelength you're using. So normally you don't have to worry about those level of details. And then the final expression for what those S1, to recall, we're really after these S1 and the S2 parameters. And so how do those relate to the Legendre polynomials? So that's given in this last set of formulas. So if you define these Legendre polynomials, if you combine them with these other polar dependencies, you can define these other functions, pi and tau. And then in its final full glory, here's the Mie equation for what those S1 and S2 terms. So what are the amplitudes of the electric fields parallel and perpendicular to the scattering field as a function of polar angle? So there you go. You get this infinite summation as a function of these depending on these functions, pi n and tau n. And once you have your S1s, you can relate these to the actual electric field amplitudes, E theta and E phi, which would be the parallel and perpendicular components relative to the scattering plane. And to give the final bottom line from Mie theory, to recall, if you take the electric field amplitude squared, you get an intensity. So ultimately, the scattered intensities that we're going to be calculating are going to be proportional to these S1 terms squared and the S2 terms squared. So there we go. So you get a computer to get these summations for you. Once you have them, you square them, and using these formulas from S2 and S1, you get the electric fields. And there you go. So here's a couple of graphs just to give you some example of what do these functions look like. They're really, similar to, they're going to have oscillatory terms. But actually they have a mix. They have oscillatory terms. For example, if you look at let's see, for example, this is the pi n functions. So if you look at pi 1, that one is actually a DC component. So you do have components in Mie theory that can model things that don't have oscillation. So that's a part that Mie theory can apply to small particles. But as you go to higher order terms, you start getting higher and higher frequency oscillations. What's being plotted here, these are these functions as a function of theta, so scattering angle. So this would be scattering angle, and this would be the magnitude of these functions, pi and tau. So you can see that they have angular dependencies. So it can be the flat, or the higher terms you put, the more oscillations you get. So let's look at some of the applications of Mie theory. This next graph summarizes 3 different scenarios, one with basically the Rayleigh-Gans and Van der Waals approximations, but now seen with Mie theory. So all of these curves represent the scattering efficiency, expressed here as a differential scattering cross-section. So essentially the probability of scattering as a function of polar scattering angle. So 0 degree would be exact forward scattering, and 180 would be backward scattering. So if we take a look at a very tiny particle, we're using a wavelength of green light, so 532 nanometers. So if we use a very tiny particle, this one is 17 nanometers, you can see that as a function of angle you get this flat dependence. So that's what we expect from a Rayleigh particle, so a Rayleigh dipole radiating, if you go along the equator. You see an even isotropic distribution of scattering intensity. So it's equal in the forward and backward. In the other extreme, if you go to a large particle, so diameter greater than the wavelength of the light, you now see the interference effects that come with large particles. So first you see this prominent set of oscillations. So those are the constructive and destructive interference patterns. And so that's one telltale sign that you have a large particle scattering. And the other one is that you have much greater scattering in the forward direction than in the backward direction. Notice that this scale here is logarithmic. So the peak here is at about 10 to the minus 10. That's about 100 times more efficient than the scattering here in the backward direction. And that's something that you will see for all large particles. So this just gives you an example of the kind of power of Mie theory. It can deal with any kind of particle size. It could be very tiny, very big, and it could deal with any wavelength and any refractive index. The refractive index is given here. M is the relative refractive index. And you notice it's written as a complex number. There's a real part and an imaginary part. The imaginary part corresponds to if the particle not only can scatter, but in addition if it can absorb light. If the particle does not absorb, the complex part is set to 0. So for the purposes of this course, we're just going to be ignoring the imaginary part. But you will see it sometimes when you look at Mie codes that are provided commercially or on the internet. They will ask you both for the real and the imaginary part of the refractive index. So for our purposes, just ignore the imaginary part. You can set it to 0. So I'm going to, for the last part of this section, I want to give you a few examples of codes, Mie codes that are available for free on the internet. This first one is from a group at the Oregon Medical Center. They have a lot of really good material on biomedical optics, a lot of courses and tutorials. And this section on their website has to do with Mie theory. They have a couple of, sorry about that. They have a couple of different, they have 3 or 4 different Mie codes that you can access from different sources. And in a minute I'm going to show you the one that they have developed, this fellow Scott Prell. He's got an interactive web page where no matter what computer you have, you can just, as long as you can access the web, you can do some quick simulations with Mie theory, which is super handy. And then the other code I want to show you is from this fellow Philip Lavin. He's got another free Mie code available. It's a little more interactive and user-friendly than Scott Prell's. But the disadvantage is that it only works with PCs and you need to download it. So if you have a PC, I'll show you in a second the basics of how to use it. Before I do the demonstration on how to use these codes, I just want to review some of the definitions of what are the results that these codes give you. So I mentioned when we looked at the Jones matrix for Mie theory that the important parameters are what are the Mie theory will give you the electric fields parallel and perpendicular to the scattering plane. And once you have the electric fields, you can get the intensities by squaring that. So this diagram over here summarizes what most common Mie codes that you find online will provide you. So the final result, if you shine polarized light onto a scattering particle, is it will give you the perpendicular polarization and the parallel polarization intensities. And these parallel and perpendicular intensities are defined relative to the scattering plane. So if you look, for example, at this case, if the light is coming along the table and scattering at a polar angle theta still on the table, so the table itself would be the scattering plane. So, but here we have a polarizer that's polarizing the light vertically, which would be perpendicular to the scattering plane. So in this case, the intensity of light under this geometry would be I perp, corresponding to the electric fields will oscillate vertically, perpendicular to the scattering plane. And then in this other scenario, we have the opposite. We still have the same polar scattering angle, but now the polarization is parallel to the table, and then it's also parallel to the table on the detection side. So these are the two scattering functions that are going to be given by most ME theory codes. And an example, it's a little hard to read. I'll show some that are a little clearer in a second. But basically this is another one where you show the scattering angle, forward scattering versus back scattering. And the green and the red curves correspond to I perpendicular and I parallel. So you can see that for forward scattering, a lot of particles have exactly the same, but as you go closer to side scattering, you start seeing a difference, which is related to the donut that we saw for dipole scattering. All right, so for the last part, let's go ahead and look at some of those codes online. So let's start looking at the one from Scott Prall's group at Oregon Medical Laser Center. So this is his web page, and there we go. So this is his the main interactive phase. So it's pretty simple. All you have to do is put the diameter of the particle, the wavelengths of the light that you're using for scattering, then the two refractive indices, the one of the medium, if it's vacuum or air, you can leave it at 1. And in this case, he's got probably a glass or a plastic sphere with the refractive index of 1.5. So that's the real part of the refractive index. And the imaginary, we're leaving it at 0 because there's no absorption. Okay. And then these last two are not really that crucial. You can just leave them as they are. This just tells you how many data points it's going to break between forward and backward scattering. So you just punch in your numbers, and then you say calculate, and bingo. It gives you a bunch of tables with parameters. I'm just going to scroll down to the graphs, and you can see here, this would be, this side would be forward scattering, this is back scattering, and you can see this is on a regular, not a logarithmic scale. This is like a plane scale. So you can see that with a 1 micron particle, and we're scattering, I think it was red light, right? Yeah, so we're using a Heaney laser, 632.8 nanometers. So red light scattering from a 1 micrometer particle. The particle is greater than the wavelength of the light, so it's going to be mostly forward scattering and with some interference effects. And then parallel and perpendicular, these are the two intensities I was just talking about, whether it's in the geometry that we're looking at, parallel to the scattering plane or perpendicular. And as you go around, this would be the polar scattering angle. It's more common to show these graphs on a logarithmic scale so that you can actually zoom in on these really small features and you can see the interference effects better. So that same plot, if we show on a log scale, you still see the high forward scattering peak, but now by zooming in the log scale, you can now see the subtle oscillatory interference effects that come from there being a large particle scattering. And again, we have the green and the blue corresponding to parallel and perpendicular geometries. Let's see if we try smaller particles. If it's let's try a 50 nanometer particle. So like that. It likes that. Okay. So here we go. Here's a smaller particle, and now you can see this is more like a dipole, like a Rayleigh dipole, right? So if we look at one of the geometries, the perpendicular, you see this almost perfect circle corresponding to that would be like the equator of the donut. And if we now excite with the other polarization parallel to the scattering plane, you now get the blue pattern, which would be kind of the cross-section of the donut, where this would be the hole going into the center of the donut, and the dipole would be oscillating like this. So there we go, pretty powerful theory. And the last thing I wanted to show you was that other website from the Philip Levin. So this is the interface for the Philip Levin code. It's more user-friendly. You have the parameters displayed over here, and polar plots are going to be shown at the bottom. So again, you're going to be having the parallel and the perpendicular scattering intensities. In this case, as shown as that S term, S squared, so that's proportional to the scattering intensity. So let's go through some of the parameters we can change. Let's try to reproduce what we did before. So we had before we had a 1 micron particle, and the wavelength was a Heaney wavelength, so 632.8 nanometers. This again is where we put the real and the imaginary parts of refractive index. So the imaginary part is set very close to 0. Sometimes codes get mad if you put actually 0 in there, so I'm just going to leave it at the default value, a very tiny value. Right now it's got a real refractive index of water, 1.33, so we can try that. Polarization, you can choose which ones you want to show. Do you use unpolarized light, or you want each one individually, or you can show both. And then this is a range of polar scattering angles. Right now it's going all the way from 0, so forward scattering all the way to back scattering. And this is just the step size in the angles, and whether you want a linear or logarithmic scale. And again, you also have different ways in which you can plot the data. Right now it's doing intensity versus scattering angle, but you can have the phase function, you can have it versus wavelengths, you can do all kinds of it's a very nice interface. You can do a lot of different plots. So let's go ahead and do that. So once you have all your parameters, you just hit new plot, and there we go. It calculated the scattering function. So again, you see forward is at 0 degrees, so it's the particle is greater than the wavelength, so it's going to be more forward scattering than back scattering. And also because it's a bigger particle than the wavelength, you're going to see some of the oscillations due to the interference effects. And if you all remember the experiments we did in class, if particles or scatterers get bigger, the fringes get closer together. So let's try if we go from 1 micron, we leave everything the same, but we just make the particle bigger. We go to 10 microns. And then now when we recalculate, there you go. You have the oscillations are much closer together. So qualitatively, it's the same effect we saw, like scattering the laser beams from a hair or from a wire or from little circular apertures. We get the same kind of dependence on how the fringe distances correspond to the size of the scattering object. So that you should always carry that as an intuition of what happens when objects on the order of the light wavelength or bigger scatter. They will give interference effects. One last thing I want to mention, which is handy about this particular code, is that you can save the data. If you go to File, you can save the results as a text file, and then you can plot them yourself in MATLAB or Excel. So it's also a nice perk of the code. All right, so that's where we're going to stop with the me theory.